Welcome back. So we'll continue with our treatment of the mass transport problem. At the end of the last segment, we took a detour to understand boundary conditions in a sort of unified picture, right, across different problems. And that's a fairly useful exercise. We'll proceed now and return to our mass transport problem and put in what is the missing component in it, which is constitutive relations for the flux. Okay, so all right. So the question we are asking is that in the context of the mass transport problem, we've introduced the flux, and what is it given by, right? How do we relate it to the primary field, the concentration? The way this is done in the context of mass transport is actually to go back to the thermodynamics, and we'll do that. The foundation of the problem comes again from this idea of the free energy function. Okay, so we start out with the free energy density function. Okay, and as we've been doing before, we'll use the symbol chi for it. Okay, and now because we are doing mass transport in isolation of mechanics, we have only the concentration as our primary field. So what is done is to say that the free energy depends upon the concentration. You may think that we're looking at a purely chemical system here, and therefore everything is defined by the concentration. All right. So this is the situation we have, and in this case, I should emphasize that when we write chi, we are talking about the free energy density function defined. This thing is defined per unit volume. All right, good. And now we want to relate the flux to it. The way this is done is to do the following. We have the free energy density function, but from here we go on to defining a free energy functional. Okay, so we define the free energy functional and we do this in pretty much the same way as we did for nonlinear elasticity. This is done by saying that for the free energy functional is for this problem of mass transport is I need to come up with a symbol for it. Let us say for now that I'm going to call the free energy functional G. It's a functional of the concentration field, and it is defined as simply the integral over the volume of our free energy density function okay, as simple as that, right? So really we're talking here of the total free energy of the body, right, of the body of interest. All right. So let me state that this is the total free energy of the body. And really, though I'm saying total free energy, it's a total free energy in the chemical context, right? So it is the total free energy of the body. I should probably extend this to say considering only chemistry. Okay, so we have a phenomenon that is driven by concentration, so think about chemistry, and I say that it's only chemistry because clearly we are not talking about mechanics, we're not talking about heat, we're not talking about thermal effects and all those things, right? And we know that those also contribute to the free energy. Okay, so really this is the total free energy considering only chemistry. If we were to put back mechanics and thermal effects, we would say that what we are writing now is only the chemical part of the free energy. Okay, so just to set things up. Okay, what is done here is in order to get to something about the flux, we first need to define a different quantity from the free energy, and this is called the chemical potential. Okay, we define we define the chemical potential, which I am going to write as mu. Okay, and this is going to be a chemical potential which is a function of C. Okay, this is a priori I'm saying that it is a function of C. Okay. Here's how we do it. The way this is done properly is the following. The chemical potential is considered in classical thermodynamic treatments as a quantity at equilibrium. Okay, so we consider what we want to define the chemical potential, but we do this by considering an equilibrium process. Okay, so consider or really considering an equilibrium state. Okay, so since we're dealing only with chemistry here, we're essentially considering equilibrium with respect to concentration. And here's what we do now. We have our free energy functional G. We know how to, and we know that we have it defined as a functional of the function C, right, of the field C. Okay, we have this. We're going to do everything like we did before in the context of equilibrium for nonlinear elasticity. Okay, so we consider first variations. Variations on C. Okay, and we do that by saying C sub epsilon is defined as C plus epsilon W, okay, where if we define spaces just like we did before, okay, where if C, the field C, belongs to a function space S, just as we did in the context of nonlinear elasticity, where the function space S consists of all C such that C satisfies our concentration boundary condition on the relevant part of the boundary. Recall as well that our concentration boundary condition alternately is also called the Dirichlet or the essential boundary condition. Okay? So, if C belongs to the space S, then our variation W, okay, function of position, belongs to some other space that we're going to denote V in complete analogy with the way we did things for nonlinear elasticity. V consists of functions W which are now going to satisfy, can you recall, by analogy with our nonlinear elasticity problem, what kind of conditions we are going to require of W? We require that it satisfies the homogeneous boundary condition on the concentration boundary, alternately called the homogeneous Dirichlet or homogeneous essential boundary condition. Okay, so what we've done now is to define variations on the concentration. And this picture is exactly like we had in the context of nonlinear elasticity. We are saying that if we look at a 1D problem, we are saying that if that is x, suppose the body of interest goes from 0 to L, because we're looking at things in 1D, just to fix ideas. We're saying that is C. And let's suppose that we have the concentration specified at some value here. Let's suppose that that is the actual concentration. Okay, and this is C bar. That value is C bar along the C axis. Okay, just as we did in the context of our nonlinear elasticity problem, we are going to say that, all right, we now want to look at the field with the perturbation, so maybe it looks like something like that. Okay, the perturbed field is C sub epsilon, which is C plus epsilon W and the original field in red is, sorry, not U, but C. Okay, so we've introduced these perturbations or these variations just as we've done before for the nonlinear elasticity problem in the context of equilibrium. And then we say we want to consider the variational derivative of G with respect to this field C. Okay? Right, that variational derivative is written as this, right? This is just our notation, and like we did in that case, in the case of nonlinear elasticity, we say it's dd epsilon of G now evaluated at evaluated with the field C sub epsilon. We take this derivative and then we say epsilon equals 0. This is our definition of the variational derivative. Okay, and this now is easy to translate to our to the case we have here. Things are very easy. Our domain omega is fixed. We just have to consider our free energy density function chi, which now depends upon C epsilon dV, right? We take that derivative, set epsilon equals 0. Okay, that's the variational derivative. Okay, I should point out that we have a split down the middle here in the screen. Okay, so we take that variational derivative, right? And this is easy to compute because it is because of the fact that our configuration is fixed, and we can take that derivative with respect to the scalar epsilon into that integral. Okay. For completeness, I realize that I should also say that epsilon belongs to reals, just as we did before for nonlinear elasticity. Okay, so let's go ahead with this process. So this is the variational derivative, and of course for equilibrium, for chemical equilibrium, unlike mechanical equilibrium that we studied before, right? For chemical equilibrium, we require what? Remember, equilibrium is an energy which is extremized. Okay? Now we define this variational derivative for our free energy functional, just as we did for nonlinear elasticity. And if you recall things from there, we must state here that the variational derivative of G with respect to C vanishes. Okay? So it says that this derivative, which is now dd epsilon, I'll expand out C epsilon. Okay, that's the variational derivative. Now equilibrium therefore requires that this is equal to 0. Okay? What we're doing here is an extremum, we're seeking an extremum of G with respect to its field C. Okay? Easy enough to compute, all right? What this implies is that now when we take that derivative with respect to epsilon, we have integral over omega. Okay? We want to take dd epsilon of dd epsilon of chi this works out to, using the chain rule, it is the derivative of chi with respect to C epsilon, okay, times derivative of C plus epsilon w, which is of course just C epsilon, its derivative with respect to epsilon, dv. Take that derivative, remember it's an integral over omega, take that derivative, set epsilon equals 0. The extremum condition requires that that calculation on the left hand side should vanish. Okay, I'm proceeding nice and slowly here, and now we observe now that, okay, so now we take these derivatives, we take this derivative and this one, okay, and then we set epsilon equals 0. All right. So what happens is that, just as we saw for nonlinear elasticity, this just means that we are evaluating this derivative at C, not just epsilon, not C epsilon, right? Because when we set epsilon equals 0, C epsilon falls back to C, right? And the second derivative just gives us W. Okay, dV equals 0. This is our condition. Okay, right? Now, this quantity, the derivative of chi with respect to C, is what we call the chemical potential, mu. Right? The chemical potential is understood as a quantity that tells us, as the derivative indicates, how the free energy changes for every little addition of concentration at a point. Okay, tells us how the free energy density function changes with every little addition of concentration at a point, right? So it's the chemical potential, which is defined as well, as the derivative indicates, right? I don't think I need to write that. Okay, all right. So the condition we have now is integral over omega chemical potential times the variation dV equals 0 for all W belonging to phi. All right.